In this video, we're going to talk about the difference between diffusion and effusion. This difference comes in how gases actually move from one place to the other, but mathematically, we would not separate the two. If the problem says diffusion, you would say diffusion, or effusion, you would say it effuses, but mathematically, we would treat them the same way. So diffusion, which is the top diagram, is basically when a gas or even a mixture goes from an area of concentration and moves to fill a larger area and therefore the area of lower concentration. So if you look at the diagram, the one on the left, the particles are more compressed, they're closer together, they have a higher concentration, and there's nothing on the right side. You take that partition up, and the gases, because they are constantly moving, will fill the space evenly, and therefore they move from area to high concentration to low concentration until it's all the same. That is diffusion. This is like when somebody sprays perfume on themselves and it's super concentrated smelling, and pretty soon everybody gets to smell it. And you end up, or better yet, guys, the Axe cologne. Let's just put that on at home and leave it there and not put it on anymore. Because initially it's super concentrated, everybody's choking, and eventually it will diffuse across the entire room and everybody gets to smell it. This is not what we want. Now, in a lab setting, we would probably do an effusion type thing. And typically an effusion is just when gases move naturally through a small hole. So the bottom drawing shows the gas is moving through a small hole. We can measure the amount of gas in the other one and therefore measure the rate of movement. So don't forget that you have this kinetic theory of gases. The gases move in constant random motion. They're made of particles. There's no attraction to each other or container wall or repulsion. And kinetic energy is related to temperature. Okay, moving on. Here we have a simple drawing of a solute in a solvent. Let's call the solvent water. And you put something in one side because particles are in constant motion, even if they're not moving super quick like gases, they are moving and they will end up filling the space evenly. And so even though this is like a solute in a solvent, this is also an example of diffusion. Now, if you have a density that's greater, it tends to sit on the bottom, or less dense tends to sit in the top. It will still eventually move so that they're all even. Again, an example of diffusion. Typically, when we talk about diffusion, we're only talking about gases, but it can occur in solutions as well. Here we have a classic drawing in which you would never have this. So you have a container on the left with hydrogen gas, a container on the right with oxygen gas, and this thing in the middle, this is called a stopcock. So anything that holds liquids or gases back, I have a control on my motorcycle that allows me to switch from one tank to an emergency tank and allows the gas to flow through, and it's called a stopcock. Same thing when you have a burette when we do titrations. So easy to look at the green gas and the red gas. You open it up and naturally they will move from one to the other. So if you look at it in the second drawing, this guy, more gases are in the right side than the left side. That's because the hydrogen gas will move at a faster rate and therefore will diffuse faster, and therefore starts filling up the right side before the red gas can fill up the left side. But eventually, as it shows in the bottom, they will all eventually become very even. Now, we're going to talk about this in terms of mathematics and pressure, and looking at these kind of stopcock things. So if you open the stopcock, the volume starts with this side, and then the volume ends up being bigger. In this case, it's twice as big. If the volume is twice as big, the pressure of the oxygen gas will be half as much, and the pressure of the hydrogen gas will be half as much. Well, if they're half as much, but they fill the same container, then the pressure is going to stay the same. We'll talk about that a little bit later. Here's the math for Graham's law of diffusion. If they said effusion, you would just cross that out and say Graham's law of diffusion. It's the same thing mathematically. Now, when we calculate mass of one thing over the mass of the other and take the square root, we end up with one number, like 1.41. Well, if that is the formula weight of something over the formula weight of something else, taken to the square root, well, technically, this is going to be 1.41 of A, all right, A, whatever that is, which is this guy, because these are going to be like crossed like this. That is going to be that, but then it's going to be to 1 for B. So we have this ratio of 1 to 1.41 in terms of rate. The bigger the rate, the faster it's moving. Now, I have a really an example of this. And so if you're looking at a large person or a small person, typically the small person can move faster. I know that's not very PC, but we'll try to do this more in the energy form. If you have two gases in the same container, in the same conditions, and therefore they're going to be at the same temperature, well, temperature is going to be average kinetic energy. So on average, these particles have the same energy. So the particle that's a big particle, right? It's a big particle moving and hitting the wall is going to hit with the same force as a little particle. How is that possible for the big particle to hit with the same energy as a small particle? And that's because the small particle must be moving faster. So this has to be comparing two gases at the same temperature. And they always are, but just to be aware of it, it must be the same temperature. Now, with this one, again, we typically look at this as one number. It's something to 1. And the A is up here and the A is down here. Well, if we calculate something to 1, we typically like to calculate a number that is going to be bigger than 1 to a number that equals to 1. We don't like to have rates of 0.5 to 1. We like rates of 2, sorry, wrong way, rates of 1 to 2. This looks a lot nicer than this, although it says the same thing. So if we want this one to be bigger than this one, then this one has to be bigger than this one. So you put the bigger molar mass on top, the smaller one on the bottom, and that will ensure you get a value over here that's greater than 1, and it makes sense. Also, knowing that if we put the big one on top, that means we're also putting the slower one on top. And then if we put the smaller one on the bottom, that means we're putting the faster one on the bottom. I say that because you may know which one's faster and which one's slower, but may not know which one's bigger or smaller. If they give you something like chlorine and they said this one diffuses faster, you would put the 35.45 times 2 or 70.9. If it's slower, right, we'll put it the 70.9 on top and X on the bottom. If we said, oh, no, I'm sorry, we meant to say that the chlorine diffuses faster. Well, if it's faster, it's smaller. We put the 70 on the bottom. We put the X on top. And we'll have a value of like, oh, 1.16 times faster. That is technically to 1. We solve for X on top or bottom. We typically don't use this to calculate actual rate. We have another equation we can do that with. But this year we may not do that because they typically don't ask you that equation on an AP test or an IB test. It's a classic test on which you can see this because what do gases usually look like? And they usually look like nothing. They don't look like anything. They usually don't have a color. They're transparent. You don't see the particles. But if you get NH3, which is the base, and hook it up with HCl, which is an acid, this is a different kind of base. You don't get water, and a salt. But you do combine these. So the H will hook up to that to form the ammonium, and then the Cl will hook up to it for the chloride, and this is a solid. So you'll end up forming a ring where these gases, going to be the gases coming off here and the gases coming off here, and then wherever they meet, right, when the ammonia and the acid meets, it's going to form a solid. And a solid is pretty easy to see. So which one do you think infuses faster? Well, ammonia has a molar mass of 17. Hydrogen chloride, it's not hydrochloric acid, there's no water. Hydrogen chloride has a molar mass of 36.5-ish. This is bigger, this is slower. This is smaller, this is faster. And we could do the calculations of how much slower or faster it is. But eventually what happens is you'll form a ring right around here. I don't know if you can see that. And it'll start forming a ring on this tube, and you can measure the distance here and measure the distance here. And of course, the faster one's going to go farther, and the slower one is going to go shorter distance. And this will be, if we had the whole 36.5 divided by 17, take the square root of it, we would see the relative rates and therefore the relative distance. So it's a really easy demo to do. I might show this to you, but it's a nice way to see diffusion rates because it's got a very obvious output. We have several equations that, at least in this year, we're not going to deal with. One, we've already talked about this pressure equals force over area. Very much a physics math equation. It's not complicated, it's just an algebra equation. And it helps us kind of define how a pressure is made by gas particles. But I'm not going to ask you to solve this one. The other one is KE. KE is kinetic energy. It is multiplied by a constant of 3/2. Can't see it now. And RT. T is always going to be Kelvin when you're using the actual temperature. And if you're talking about SI units, then we have to use 8.31. And if we're talking about SI units, we get joules. And SI units are going to be Kelvin. So if you wanted to have, and this is only temperature dependent, 3/2 is the constant, R is a constant, and therefore the only thing that the kinetic energy is compared to is temperature. Now this is per mole, so you would have joules per mole, because what happens if you had 2 moles? Well, you have twice the energy. So this is a way to figure out the energy of a gas per mole at a particular temperature. This also says that every gas, whether it's hydrogen gas, whether it's a monoatomic like argon, whether it's a fatter one like chlorine gas, whether it's a compound like HCl gas, at the same temperature, these would have the same energy per mole. Even though this one's smaller and this one's bigger, they would have the same energy per mole. That's a lot to say for something that I'm not going to ask you. And then down here we have this RMS, which is root mean squared velocity. Velocity is actual speed. So if you have 3, which is a constant, R, which is the 8.31 constant, T, which is temperature in Kelvin, right? And then divided by M, this is not molarity. This is going to be formula weight in kilograms per mole. Why kilograms? Anyone? Anyone? Bueller? Anyone? 2 words, SI. It makes the math work. We can derive this and see how you end up with velocity, which is meters per second, because these units will all cancel out. Again, that's a lot for something we're not doing this year. It's really interesting, but we're going to have to conserve time and press on, and it's not something that's typically asked in AP and definitely not asked in IB. I hope this video helped you guys.